Deep offshore technology encompasses the tools, methods, and systems developed for the exploration and extraction of oil and gas from ocean depths, typically exceeding 500 meters, 1,640 feet. As oil and gas resources in shallower waters become depleted, energy companies have increasingly turned to deepwater and ultra-deepwater environments to tap into untouched reservoirs. These depths require specialized technologies to overcome challenges like extreme pressure, temperature variations, and isolation from the surface. In this video, we will study key technologies in deep offshore exploration and production. The challenges of deep offshore exploration and production require advanced technologies specifically designed to operate in extreme depths and hostile conditions. These technologies enable safe, efficient extraction of oil and gas while managing the unique operational and environmental challenges of deepwater settings. 1. Subsea Production Systems. Subsea trees, also known as Christmas trees. These assemblies of valves and fittings are installed on the wellhead on the seafloor to control oil and gas flow from the well. They enable remote management and are equipped with sensors to monitor pressure and temperature. Subsea manifolds. These structures gather production from multiple wells and direct it into pipelines, facilitating efficient transport and processing. Subsea boosting pumps. These high-pressure pumps help transport oil and gas from the seafloor to the surface by boosting pressure, addressing challenges like low flow rates and pressure loss over long distances. 2. Floating Production Systems. Floating production, storage, and offloading units, FPSOs. FPSOs are floating vessels used for processing, storing, and offloading oil and gas, particularly useful in remote offshore fields where pipelines are impractical. Floating storage units, FSUs. FSUs serve as standalone storage vessels and are often connected to production facilities to store oil before transferring it to tankers. Spar platforms. Tall, cylindrical structures anchored to the seabed with tension cables, providing stability for drilling and production in ultra-deep waters. Tension leg platforms, TLPs. These floating structures are anchored with tethers to the seafloor, providing stability for drilling and production, even in deep waters with high wave activity. 3. Deepwater drilling technology. Drill ships and semi-submersible rigs. These mobile, dynamically positioned rigs are specially designed for deepwater operations, allowing precise control and stability even in challenging weather conditions. Extended reach and horizontal drilling. Advanced drilling techniques that allow wells to be drilled horizontally or at long distances from the entry point, enabling access to reserves not directly below the rig. Managed pressure drilling, MPD, a controlled drilling process that maintains optimal wellbore pressure, reducing risks of blowouts and well instability in deepwater operations. Number 4. Remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs. ROVs, remotely operated from the surface. These underwater robots perform tasks such as inspection, maintenance, and repair of subsea equipment at depths beyond human reach. AUVs, autonomous, self-guided vehicles that can survey and map the seafloor, gather data, and inspect underwater infrastructure without needing direct human control. 5. Subsea pipelines and flow lines. Flexible flow lines. Specialized pipelines capable of withstanding high pressures and temperatures, designed to transport oil and gas from subsea wells to processing facilities. Risers. Vertical pipelines connecting the seafloor to floating production platforms, essential for transporting fluids from the well to the surface. Flexible risers are often used in deep water due to their ability to withstand high tension and movement. Umbilicals, bundled tubes, cables, and wires that supply power, chemicals, and control signals to subsea equipment, enabling remote management and monitoring. 6. Well control and blowout prevention. Blowout preventers, BOPs, critical safety devices installed on wellheads to prevent uncontrolled oil or gas flow, reducing the risk of blowouts and spills. BOPs are equipped with high-pressure valves and are designed to shut off the well in case of emergencies. Capping and containment systems, emergency response systems developed after high-profile incidents, designed to cap or contain subsea well blowouts and prevent oil spills from reaching the surface. 7. Seismic imaging and reservoir monitoring. 4D seismic imaging, an advanced seismic technique that tracks changes in reservoirs over time, helping operators optimize extraction by visualizing how resources are distributed and depleted. Fiber optic sensing. Fiber optic sensors installed in pipelines and wells monitor temperature and pressure in real time, offering critical data for safe operation and early leak detection. Reservoir modeling and simulation. Software tools that use real-time data to model the behavior of oil and gas within a reservoir, aiding in decision-making and extraction planning. 8. Digitalization and data analytics. Digital twins. Digital replicas of physical assets like platforms and equipment. These virtual models allow operators to simulate scenarios, perform predictive maintenance, and optimize processes. AI and machine learning. These technologies analyze large data sets to predict maintenance needs, detect anomalies, and optimize production, reducing downtime and enhancing efficiency. Cloud-based data platforms. Cloud computing enables remote monitoring and analysis of deepwater assets, allowing real-time data access from onshore locations, improving operational oversight and decision-making. 9. Environmental monitoring and safety systems. Subsea environmental sensors. Sensors placed near offshore equipment monitor conditions such as water quality, temperature, and underwater noise to minimize environmental impact and ensure compliance with regulations. Leak detection systems. Early warning systems that detect hydrocarbon leaks in pipelines or equipment, reducing the risk of large-scale environmental incidents. Marine life monitoring systems, technologies that monitor marine life around offshore installations, allowing operators to minimize ecological disturbances and meet regulatory requirements. 10. Power and energy solutions for remote operations. Subsea power distribution. Systems that provide electricity from onshore or offshore generation sources to deepwater installations, reducing reliance on surface power sources. Hybrid energy systems, combining renewable energy sources like wind or wave power with traditional methods to power remote installations, lowering carbon emissions and supporting sustainability. These technologies together form the backbone of deep offshore exploration and production. By overcoming the extreme conditions of deepwater environments, they enable the oil and gas industry to tap into new resources safely and efficiently, meeting global energy demands while maintaining high safety and environmental standards.